We are the Pantstones, and we're looking to design an assistive dressing apparatus for pants. How do you put on pants every morning? First one leg, then the other? Maybe both at once and pull? What if I told you that the first method requires a surprising degree of balance, the second method requires non-arthritic grip strength and 2 functioning hands, and both methods require bending all the way down? The picture on the left shows the most common method of putting pants on for those less physically able. A grabber for the pants to avoid bending over, followed by a minute or two of shimmying them up to the waist. This is a struggle that affects those with physical disabilities, basically everybody who gets prescribed a hip kit, and given enough years, almost everybody. The truth is, the world is designed around the average person, and the average person is young, able-bodied, and unimpaired physically or cognitively. But most of these people are also destined to reach an age where this average world also underserves them. We want to have the first product to completely automate pants dressing with zero user effort. This product won't be as flexible as something like that aforementioned grabber, and makes the assumption that if you're putting pants on, you're walking out the door, so you may as well knock out both in one daily action. However, we'll also be the first product to serve those who are less than able as opposed to the highly competitive market for serving the totally infirm. And while we're unlikely to be the cheapest or most successful product to ever serve this need, we hope that any success will spur similar innovation and competition in the domain of products which augment user independence. Here we have our top customer requirements. They mostly boil down to put on pants without any user effort or particular ability beyond attaching pants, standing up, and pressing a button. Here are all of our identified product functions. Those in bold were refined further as a group using the 635 method in order to assist with design ideation, but also important considerations in our concepts were supporting user balance and engagement and disengagement methods. This is a list of engineering characteristics we developed, which we believe effectively quantified all relevant performance metrics during the solution-neutral concept development process. But despite solution neutrality, there were universal constraints we needed to consider for any design. We decided to design our minimum max load case around the 95th percentile male, as this would include more than 95% of the population. This meant we needed to support that weight, which would be 98 kilograms, and actuate to that waist height, which would be 122 centimeters. This is also a household object, so it had to fit through US building code doorways, and needed to be a reasonable weight for an able-bodied person to manipulate if assistance was required. This finally leads us to our list of decision criteria, or the set of quantitative and qualitative characteristics we used for methodological concept analysis and comparison.
So now I'm going to discuss our team's concept development process. So as a team, we created a concept chart that was comprised of the best physical designs for each concept function. Our concept functions are listed on the chart. And so in order to come up with a final concept design, each team member brainstormed a new design that incorporated all 3 product functions. And in this updated chart, you'll see the combinations of designs that each team member chose based on the color code. And also because some team members have similar ideas, they work together to narrow down their concept design. So now I'll be showing each new concept and discuss how they're appropriate and distinct from the others. So in this concept, there's a button that controls the movement of the apparatus, the contour springs bring the pants up, and the motors bring the pants down. So this could also help take the pants off if needed. And this is the only design that uses springs. And this design, it's roofless and adjusts the width of the machine that's automated, and it also uses a pulley and motor system. And this design, there's a main structure made of 2 disconnected stands that allow the structure to be adjusted, and it also utilizes a pulley and motor system. In this design, there's a winch and pulley system and a roller on rails for constraining. And lastly, in this design, it's a lead screw connected to a motor that lifts the apparatus, and a linear motion shaft that constrains the motion. So after drawing each new concept, the team discussed each concept design in depth using the Pew analysis and the Pew chart. So the first concept is a baseline, and the other concepts are compared to the first one. So it's a plus, it means it has more potential, a minus sign, it has less potential. So at the end, we added the pluses and minuses, and we determined that the final 3 that's highlighted in green was the most advantageous than the others. So this is how we were able to narrow down from 5 concepts to 3 concepts. And so now Jennifer will discuss these 3 concepts in detail.
So I will be talking about our final 3 designs. The first one consists of 2 wall frames made out of plastic attached to metal handlebars on the top. There is a DC motor connected with pulleys on each side of the frames. The bottom rectangular pieces use lead screws to slide in and out, and the person can use both controllers on either side to adjust the lower width of the structure, as well as adjusting the pulleys. There are 4 clips that attach to the pants, and the entire frame is foldable for easy storage. The second design is made out of steel uni struts. On the top, there is a winch that connects the pulleys with the DC motor on the bottom of the structure. There is a steel frame that slides up and down along roller bearings, and there are molded steel bars attached to the frame to attach the pants with the clips. The frame can be controlled using the up and down buttons on either side of the handlebars. The whole structure could be easily disassembled by taking the bolts off of the struts. And the third design is made out of 2 freestanding pillars. There are 2 systems of pulleys with 2 DC motors. The motors are located on the aluminum struts at the bottom half of the structure to lower the center of gravity, allowing for a more stable design. The pillars can be adjusted through locking pins, and the pants can be attached with clips to a metal bar that will be in the middle of the 2 pillars. The bar is shaped as a half square and is attached to the pulleys, and the user will be able to control the movement of the pulleys and the handlebars through Bluetooth.
For the final concept selection, our overarching goal was chosen to be put pants on. The reason we chose this as our goal was, as a team, we believed it best fit the problem that our product is being designed to solve. With this overarching goal in mind, we chose what we believe are the 3 most critical design criteria that must be considered. These 3 criteria deal directly towards our targeted customer base, which will be made up of older and weaker individuals. Safety and ease of use touch on these aspects of our customer base almost exclusively, and we felt that these 2 criteria design would be most appreciated by our targeted customer base. Cost was also a very important design criteria that we believe needed to be considered. As our team wants to keep the cost of this product down to allow it to reach a wider customer base, cost must be considered during design. After going through the first steps of the AHP, we came to the conclusion that the rankings are safety, then ease of use, then cost based off of the averages found. The first design criteria that was looked at in our AHP was safety. With this criteria being our most important one, we took great care in making sure the concept-to-concept comparisons were done thoroughly and accurately. When all was said and done, it was revealed that Concept 2 was by far the most safe concept that we had come up with, while Concept 3 was the least safe. The second criteria we chose to look at was the ease of use aspect. We again made sure to perform the concept-to-concept comparisons thoroughly and accurately. After performing the various calculations for these concepts, we found that Concept 1 was by far the best concept when it came to ease of use. The third and final criteria we chose to look at was the estimated cost of each concept. From previous on-hand knowledge, as well as various websites like McMaster-Carr, we were able to determine an accurate estimated cost for each concept, which factored into the comparisons. When all was said and done, Concept 1 came out to be the cheapest option by a large margin, which is reflected in the final averages. Once all 3 individual design criteria were analyzed, the results were all pulled together and the AHP was finished to find the aggregated weights for each concept. After performing the calculations for these weights, it was revealed that Concept 2 would be our team's chosen concept, with Concept 1 coming in a close second.
For the safety criteria, we said that concept number 1 was moderately unsafer than concept number 2 because concept number 1 had a frame at the bottom, which poses a tripping hazard for most users, as well as exposed wires when the user is going to put on pants. We said concepts 1 and 2 are safer than concept number 3 because concept number 3 has the user adjust the height and width of the apparatus for their desired fit, which can pose a tipping hazard because concept number 3 isn't tied down to anything. They're freestanding. We also said that 1 and 2 are safer because it accounts for all the user populations, but concept number 3 only accounts for the younger populations due to the physical effort that has to be put in. to moving the apparatus around. For the ease of use category, we said that concept 1 is easier to use than both concepts 2 and 3. And we said this because concept number 1 has less user interaction and is more automated than both concepts 2 and 3. Concept number 1 uses a D-pad interface with a up and down arrow key to account for the motion of the up and down movement of the pants, and the left and right arrow keys to account for the adjustable width of the apparatus. And for the cost criteria, we said that concept number 1 costs less than concepts 2 and 3 because concept number 1 is made of plastic versus concept 2, which is made of steel, and concept number 3, which is made of aluminum. And it is easier to manufacture plastic than aluminum and steel.
This was the final concept that our team chose for our project. The unique aspect of this design is the cantilever design, which helps prevent tangling with wires compared to concept 1 and 3. This design utilizes a single electric motor and a winch and pulley system to raise and lower the pants holding apparatus, decreasing complexity and cost compared to the 2 motors required for the other concepts. The wire is connected to a lifting mechanism for the pants that is constrained with a roller rail system only allowing for vertical motion. Some other critical features include large diameter balance bars to accommodate for people with arthritis, control switches on both sides for left and right-handed users, and a self-adjusting claw to accommodate for different pant sizes. We believe that this concept is truly the best method for solving our problem for the following reasons. It was the highest ranked in the Pew chart based on our decision criteria. It was the highest ranked in the AHP based on our 3 most critical design criteria of safety, ease of use, and cost. Finally, we believe this design is the safest design due to the nature of the cantilever design. This design allows for a sturdy base without the addition of a tripping hazard like in concept 1, and the pulleys and wires don't act directly on the pants like in concept 1 and 3, which could be a tangling hazard as well as a pinching hazard. The concept strengths that this design has is that it is easy to use. There are only up and down controls, and the claw allows for easy adjustability for pants waist size. This design also incorporates a couple safety features. First, it has a plastic guard to cover most of the moving components, and the motor is mounted low for low center of gravity to resist tipping. However, this concept has a couple weaknesses. The first being that the claw design is pretty complex and may be harder to manufacture and design. The second weakness that we want to focus on is the size. The size of this concept is fixed, unlike concept 1 and 3, and the overall volume can't be changed easily, so storing this design could be hard.
Thank you for watching our presentation on this assistive pants dressing apparatus, and we look forward to getting your feedback.